Right, so in this video, we're just going to talk about some basic trig identities. Some of these we've already talked about, but we're going to formally introduce them now. And then others I've hinted at, perhaps, but we haven't formally talked about yet. So, before we get into an identity, though, does this make sense? Pause the video, unpause when you're ready to discuss. All right, hopefully you said this was unreasonable. However, I will point out, this algebraic mistake right here is one of the most common algebraic mistakes that I see, which is frustrating because it's obviously not true when we see counterexamples of it, right? So a true statement is that 3 squared plus 4 squared does equal 5 squared. This is absolutely true. We also know of this from a 3, 4, 5 triangle, but this is a true statement. If I take that same statement, 3 squared plus 4 squared equals 5 squared, and I take the square root of both sides, and I treat it as 3 plus 4 equals 5, this is not true, right? And that's essentially what Dave, if that is even his real name, did here. So we can't just square root each term individually. I am allowed to take the square root of both sides. This is still a true statement, but this is a false statement. So I can't go from the blue and the purple here to the black. That is false. All right, so let's talk about some identities. One set of identities is the reciprocal identities. This is something we have definitely talked about quite a bit so far in this trig course. However, we haven't formally written them out. So these are what we call the reciprocal identities. There are 6 of them. However, notice that sine of theta equals 1 over cosecant of theta, therefore cosecant of theta equals 1 over sine of theta. This is essentially the exact same identity, just rewritten, right? Same here. Cosine of theta is 1 over secant of theta is 1 over cosine of theta. Same exact identity, just rewritten. And when I mean rewritten, I mean using a little bit of basic algebra, you can go from this form of the identity to this form of the identity. And then here, tangent of theta equals 1 over cotangent of theta, and cotangent of theta equals 1 over tangent of theta. Again, basically the same thing. We just do a little bit of basic algebra to go from one to the other. Now, let's back up a second. What does it mean for something to be an identity? This is very important for us to understand. In order for something to be an identity, it means that in this form, it is always a true statement. So if I do a little bit of algebra to this, and I do correct algebra, there's nothing wrong with that, but it might not be an identity anymore. It might, but it might not. So that's just something to keep in mind. The other thing I want to point out with the reciprocal identities is these identities hold true to any power. And so what I mean by that is if I was to take this and let's say square both sides, this is still a true statement. So sine squared of theta equals 1 over cosecant squared of theta. That's a true statement. If I raise something to the third power, that's still a true statement. So tangent cubed of theta is 1 over cotangent cubed of theta. So those are still identities. And I can raise it to any power and that will still hold true. So that is something to keep in mind about the reciprocal identities. Okay, now quotient identities. Again, we know that, or we have talked about these a little bit. We just haven't formally introduced them really, but I have definitely emphasized this, especially when we talked about the unit circle. Sine is the y coordinate, cosine is the x coordinate, tangent is y over x, so it should make sense that sine of theta over cosine of theta is the same as tangent of theta. And same with cotangent of theta is x over y, so that's cosine of theta over sine of theta. This should also make sense from a right triangle trig point of view. If I draw a right triangle and I call this theta, and this is the opposite then, and this is the adjacent, and this is the hypotenuse, well, I know sine of theta is the opposite over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse. And if I divide sine of theta by cosine of theta, then that would be dividing the opposite over the hypotenuse by the adjacent over the hypotenuse. And if I multiply the numerator and denominator by the reciprocal of the denominator, it'd be hypotenuse over adjacent times the hypotenuse over the adjacent. Those cancel out, the hypotenuses cancel out, and oh my god, look at what do we get? We get opposite over adjacent. What's the opposite over adjacent? That's the tangent of theta. Okay, another thing I want to point out with the quotient identities, similar to the reciprocal identities, these hold true for any power. So if I say, let's raise both sides to the fifth, then the cotangent to the fifth power of theta is going to equal the cosine to the fifth power of theta over the sine to the fifth power of theta. So, and the same is true with the tangent of theta equals sine over cosine of theta. That holds true no matter what power we raise these to. Another thing I want to emphasize, I keep emphasizing those little things, is you will notice as I'm talking, sometimes I get a little lazy in my speech. I'm trying not to, but sometimes I do, and sometimes I might just say tangent equals sine over cosine. Keep in mind, tangent without an input is nothing. Same with sine without an input or cosine without an input. They have to have an input. So I'm talking, I'm just getting a little lazy. However, when I'm saying tangent equals sine over cosine, I mean tangent of theta or tangent of x or tangent of, pick your favorite variable, equals sine of that variable over cosine of that same variable. Okay. The other thing to point out, and this should hopefully be kind of obvious, but maybe it's not, is the variables have to match up in order for this to be true, right? If this is tangent of theta, and then this doesn't equal sine of x over cosine of x, that's not true. Tangent of theta equals sine of theta over cosine of theta. Tangent of x equals sine of x over cosine of x. All right. All right, and last but not least, we have our Pythagorean identities. And so, again, I did talk about this a little bit earlier on, but we know, or now you know, sine squared of theta plus cosine squared of theta equals 1, tangent squared of theta plus 1 equals secant squared of theta, and 1 plus cotangent squared of theta equals cosecant squared of theta. These should make sense because of our Pythagorean theorem. So if you want a little proof, which I know you do, because you are all sending me messages saying you need more proofs, right? That's what everybody loves to see. If I call this opposite, and this is adjacent, and this is hypotenuse, then I know from the Pythagorean theorem that, the opposite squared plus the adjacent squared is going to equal the hypotenuse squared, right? That's Pythagorean theorem. But what if I just take this and I divide everything by hypotenuse squared? I can do that. That's how math works. What's the opposite over the hypotenuse, though? Oh, wait. No kidding. That's sine. So this becomes sine squared of theta. Adjacent over hypotenuse is cosine squared of theta. And anytime we divide two things that are exactly the same, we get 1. Right? So that's how we get this Pythagorean identity. Now, if I know that Pythagorean identity, and I know my reciprocal identities and my quotient identities, it's really easy to understand where I come up with these other two Pythagorean identities. So for instance, and I could do this a couple of different ways. I could take the exact same triangle that I have here, the exact same Pythagorean identity, Pythagorean theorem that I wrote down here, and instead of dividing by hypotenuse squared, I could divide everything by adjacent squared, or I could divide everything by opposite squared. Another way to do this, and this is what I'm going to show you, is I'm going to take this first Pythagorean identity. So sine squared theta plus cosine squared theta equals 1. We know that is true, right? So I'm just going to rewrite it. Sine squared theta plus cosine squared theta equals 1. And I'm going to divide it all by sine squared theta. Why? Because I can. Why not? So what is anytime I divide two things that are the same? That's 1. What's cosine over sine? Cosine of theta over sine of theta. What did we say that was? Very good. Cotangent theta. But it's squared, right? So this is going to be cotangent squared of theta. And then 1 over sine of theta is cosecant of theta. So 1 over sine squared of theta is cosecant squared of theta. That's our Pythagorean identity. Same thing, again, I'm going to start with my first Pythagorean identity. So I'm just going to rewrite sine squared of theta plus cosine squared of theta. Whoops, not plus, equals. Equals 1. And now, instead of dividing by sine squared, we're going to divide by, you guessed it, cosine squared of theta. And so now I know that sine squared of theta over cosine squared of theta, that is tangent squared of theta. Anytime I divide two things that are the same, that's 1. And 1 over cosine of theta is secant of theta, so 1 over cosine squared of theta is secant squared of theta. Other thing I want to emphasize, I know it's getting good on these identities, is they can be rearranged. So for instance, and I'm not going to show you this with all of them in every possible combination, but if I take sine squared of theta plus cosine squared of theta equals 1, if I subtract, let's say, sine squared of theta from both sides, then I end up with cosine squared of theta equals 1 minus sine squared of theta. That is also true. If I instead had subtracted cosine squared of theta, I also know that sine squared of theta equals 1 minus cosine squared of theta. Also true. And I could do that with this Pythagorean identity or this Pythagorean identity as well, where I can rearrange the, algebraically rearrange the order in which they are written. All right, so those are our basic trig identities. There are a lot of other trig identities, but if you understand these, this will allow you to do most trig. So by these, I mean the reciprocal identities, the quotient identities, and the Pythagorean identities. Those are big. And again, it's not about memorizing a bunch of unique identities. Hopefully you recognize and understand that there are patterns. They all relate to still our right triangle trig, which also relates to our unit circle. So again, that's one of the really nice things about trig is if you actually try to understand it, you see that it's not a bunch of unique pieces of information. It's just a few concrete pieces of information you need to know, and then you can create from there circles and triangles and graphs and algebraic equations, but with trig in them, or algebraic expressions, but with trig in them. And it's really kind of a cool thing. That's my spiel.